And some solved problems for chapter 21. Very hard concept is that of induction. If you think about this magnet for a second, it's going to have a magnetic field that's going to be coming out of the north end, kind of maybe wrapping around, coming into that south end. Take a look at this loop right here. If we were to take this magnet and start putting it into this loop, then it's going to be increasing the flux. Nature doesn't like that. Nature says, I want to oppose this change, and so I'm going to essentially try to create a magnetic field that's in this direction right here. Now, how do I get that magnetic field? What you can kind of do is say, let me just take a look at this wire right here. I'm going to point my thumb in this direction. What direction do my fingers curl around it? Well, they're going to curl around it in this way and come out of the wire, just like I would expect my induced magnetic field. So that tells me that the current has got to be flowing like this, flowing through this resistor from the right side to the left side. Again, opposing the change. And now some more practice with induced EMFs. Suppose I have a coil of wires right here, and I've got some magnetic field that's initially pointing in the upwards direction, so it's going to look like that. We just go ahead and say up is explicitly going to be positive here. Now, some time later, so delta t, magnetic field is going to be pointing down. So at the end of the day, it's going to be looking like that. We've changed the magnetic field, we've changed the flux, so we have therefore induced an EMF. EMF, change in flux over change in time. And the negative sign really just tells you a direction. We don't care about that right now because it's not asking for the direction. We just want the magnitude, so I'll just leave that off. So flux is defined to be equal to the magnetic field multiplied by the area over our change in time. And in this case right here, our area is not changing. So I'm just going to go ahead and pull that guy out. So area, change in magnetic field over the change in time. And the area is just going to be pi r squared. Change in magnetic field is going to be magnetic field final minus magnetic field initial, or magnetic field 1. And delta t, I just know that. So now I know everything. So very simple matter of plugging in. Pi multiplied by the radius is going to be 0.108 divided by 2. Make sure you square that guy. Magnetic field final, again, that's going to be explicitly negative. So negative 0.25 minus 0.48. Delta t, 0.16. Go ahead and I calculate all this stuff out and ignore the negative signs because that's just direction. And I'm going to get 4.2 times 10 to the negative 2 volts. And just a little bit more practice with induced EMFs. Here we have this figure right here. And in this case right here, the flux is changing. The area is getting larger. And so there's going to be an induced EMF. The induced EMF in this case is going to be equal to the magnetic field multiplied by the length multiplied by the velocity. So 0.8 Tesla multiplied by the length, 0.12 meters, and 0.18 meters per second. And the induced EMF is going to be 1.73 times 10 to the minus 2 volts. And some problems with transformers. Transformers are relatively straightforward. Takes a primary voltage, turns it into a secondary voltage simply by having a different number of turns. We're told that number of turns in the primary is 148. We're looking for that in the secondary, so kind of listed all that. Forgot my units. Very simple relationship. The ratio of the voltage of the secondary to the primary is going to be the same as the ratio of the number of turns. So this is what I'm interested in, so a little bit of algebra later tells me that the number of turns in the secondary is going to be equal to the number of turns in the primary, and then the ratio of the voltage in the secondary to the voltage in the primary. So 148 multiplied by the voltage in the secondary, 13,500, divided by 117. So the number of turns in the secondary is going to work out to be 17,077 turns. And lastly, some application of power in a transformer. We know that the output voltage is going to be 12 volts. So that tells me that I'm looking at the voltage in the secondary there. It tells me the input current is 12 amps, so that's going to be the current of the primary. This is a 95 watt transformer, so the power is going to be equal to 95 watts. one thing to keep in mind is this is going to be the power in the primary as well as the power in the secondary. Really, this is about conservation of energy, because power is just energy over time. Now what I'm interested in is this a step up or a step down transformer? Is the voltage higher in the primary or higher in the secondary? So I need to find out what the voltage in the primary is. I know I can write the power is going to be equal to the current multiplied by the voltage, both of these in the primary. So the voltage in the primary must be equal to the power rating of this transformer divided by the current on the primary side. So 95 watts divided by 25 amps. That's going to give me a voltage of 3.8 volts. So that tells me that this is going to be a step up transformer, because I'm taking my 3.8 volts and I'm stepping that up to 12 volts. Now I'm looking for the what factor it changes the voltage by. Very simple. Voltage in the secondary relative to the primary is going to be equal to 12 volts divided by 3.8 volts. So it's going to step it up by a factor of 3.2.